Okay, so welcome to lecture 4 of our CS2 classes. And as you all are aware, in the last lecture, we did go through some. So in the previous lecture, we went through gamma distribution and we learned about the coolest function, probably the gamma function. And then we had a look at the MGF of a normal distribution. And the only important thing to take from this slide, I would say, is the method of completing the square. So instead of getting bogged down by this monstrous looking integral, what you should always try to do is try to see the commonalities between the integrals that you have to figure out and some integral which might already exist. So the one thing could be, to look at the powers of E and how they behave and compare this with the distributions, the PDF of the distributions that you already have. And again, the important thing would be the limits here, because if these limits would differ, then the PDF of this integral may or may not be 1. So it is 1 only if it is defined over all the values that your x variable can take. And which is what happens here. And thus you can easily figure out the MGF of the normal distribution, which is just this. And next up, we studied something about log normal distribution, and we saw the changes in the domain of the values that log x can take and the values that x can take, where log x follows normal distribution, but x follows log normal distribution. And yeah, that was about it. And then we again had a look at how to figure out the moments of log normal distribution. And we'll learn much more about moments in today's class, which would be one of the methods to figure out something which you will most likely be doing, in a real-time scenario. So you're given some data and you have to figure out what kind of a distribution would fit best. Rather, to start with, not even the best, just which distribution will fit. So when I'm talking about, let's say, the normal curve, I know that when I'm talking about a normal distribution, it is not just one curve. It is a family of curves where each of the family is defined by the different values of the parameters mu and sigma that it can take. So again, we'll try to learn how to determine best what should be the value of mu and what should be the value of sigma in particular cases in today's lecture. So we talked about moments of log normal distribution, and then we had a look at another distribution which goes by the name of Pareto distribution. Did any of you search about the Pareto principle or the rule that I was speaking about in the previous lecture? Anyone? No? No problem. So it's not much of importance maybe because this Pareto distribution, knowing about the Pareto rule may not count in those 20% of things, which might give you the 80% of the results, or it might. So it's up to you again. And then next we looked at the generalized Pareto distribution. So the difference being here we looked at 2-parameter Pareto distribution. The first parameter is alpha and the second parameter is lambda. And here in the generalized, we had an additional parameter k, which added to the flexibility of the distribution. And therefore, you know that the PDF can take even more varied values than it could have taken in the previous case. And I guess it was homework and most of you guys did WhatsApp me with the correct answers. So that made me really very happy. And it was like instantaneously messaging. So that was good as well. So we figured out the expectation of X. And now I hope you guys have had enough practice to, figure out these kind of stuff. So again, here you're doing the same trick because for Pareto distribution, we define X to be greater than 0. We take values from 0 till infinity. And we have some PDF already. So basically we made this into a PDF by adding and by multiplying and dividing it by some stuff. And we tried with various parameters, and these were the parameters we converged to. which would work best here. So we got this value for the expectation of x. And can someone remind me what is the value of expectation of x squared? Just by having a quick look into your books. Can you tell me what was the value of expectation of x squared that you guys got? I think it was somewhere like lambda squared times k plus 1 upon alpha minus 1 and alpha minus 2, right? And then you also go on to figure out the variance, which will be something like this. Right? So do you guys like black screen better or white screen better? Or there is no preference and you're fine with anything?
White.
White? Okay. So we'll go with white. Perfect. So let us start with studying some another distribution again, which goes by the name of Burr distribution. Has anyone heard of this distribution before?
No, ma'am.
Seen it in the table booklet.
Seen it in the table booklet, right? So even I haven't seen much of applications of this Burr distribution, but again, it is just one of the transformations that is applied to the Pareto, which is most likely is. So from the previous slides, we do remember that the PDF for our Pareto distribution is something like this. So we have 1 minus lambda raised to alpha upon lambda plus x raised to alpha. And again, this is only defined for all x's which are greater than 0. So what happens is, to add again some sort of more flexibility whenever you require a fit to a particular data set. So sometimes what happens is you are given a data set and you know that this Pareto quite doesn't fit well. So what you try to do is you try to add in some extra parameters and give it some more flexibility so as to account for the little variation that only this Pareto cannot take into account of the data that we have at hand. So this is for Pareto. So what happens in Burr is that this x here is raised to 1 in Pareto. So in Burr, you will add some variability to that x by raising it to some gamma. So essentially, Burr will have 3 parameters: lambda, alpha, and gamma. So that's it about the Burr. And again, I would suggest for you all to, try to derive the mean of this Burr distribution. And then what you can do is you can check whether the mean of this Burr distribution is equal to the mean of the Pareto, this Pareto, not the generalized Pareto that we derived. So you will probably have to figure out the mean for this guy as well. And when you substitute gamma as 1, the mean of this Pareto, when you substitute gamma as 1 for the Burr, you should get the answer for the mean that you got for the Pareto distribution. So I guess this would be the homework for each one of you. So again, just to remind you guys, so try the mean of Burr and show that it's equivalent to Pareto's mean at gamma equals to 1. Okay, so I hope you all are comfortable as of now with the integration and all that we have to carry out. But again, just try it, and if you get stuck anywhere, WhatsApp is to your rescue and you can message me anytime or WhatsApp in the group as well. So it's not a big deal. Even other classmates of yours can help you if need be. So, okay. I think that was it about the distributions, which are, I mean, so there is one more distribution actually that we must see. Have you guys heard of Weibull distribution? Anyone heard of Weibull distribution? No, still seems new, but let's see. I think the way we write Weibull distribution will again seem a bit familiar to you guys because it is nothing but, just some flexibility added to the exponential case. So right now what we saw was Burr distribution, which added a bit of flexibility to the Pareto case. So what happens here is, maybe even before discussing the Weibull distribution, let us have a look at exponential and Pareto distribution. So again, whenever I'm talking about exponential distribution or Pareto distribution, or I'm going to talk about the Weibull distribution, the thing that matters the most in these cases is how the tail behaves and how these distributions converge as in when you increase the x value. So let us say I have this one graph where I'll have on my x-axis some values that my x will take, okay, and I'll have some PDFs plotted on my y-axis. So let us try to plot the exponential graph first. And to even plot the exponential graph, again, what we are trying to look at is, this is the crucial step. So if I'm talking about, let's say, exponential, and I'm looking at the probability that my x random variable takes some value which is greater than this small x. So can anyone tell me what should the formula for this guy be? What is the formula for exponential here?
Is it e raised to minus lambda?
Yeah, it is exactly that. So it will be e raised to minus lambda x. And for Pareto, it will be something like this. So again, we are looking at this. So the chance that it takes a value greater than certain value x, so that will be something like this, lambda of 1, lambda plus x, and everything raised to the power of alpha. So whenever I'm looking at things like this, again, we can have two sorts of tails, right? So one could be one could be the upper tail and the other could be the lower tail. So here what we are looking at is the upper tail, which corresponds to this area of the graph. So what I'm going to do here now is plot this exponential function and plot this Pareto function. So again, can you guys have a wild guess at which tail should be heavier? So by heavier, I mean, let's say if there is one tail, which is like this, the heavier would be the one which assigns more probability to the outcomes than this one. So any guesses? So what you will have to do is you will have to compare for each x the value of this and the value of this. And lambda you can make the same. So lambda should be the same when you're comparing these two. Any guesses? Anyone? Can you even compare these two? with the information that I have provided to you guys?
I'm just a guess, the lower tail.
The lower tail would be for exponential or for Pareto?
Pareto.
Pareto. And why do you think so?
It's just a guess.
Just a guess. Okay. Okay. So again, remember, any guess that you make should have some sort of logic at least behind it. So it may be right, it may be wrong, but whenever you're asked to guess, at least when you're dealing with statistics, you know that there are some parameters which you can maybe compare, maybe not. So the answer could be uncertain as well. But again, just try to be mindful, and it's okay to just guess for the sake of guessing. But then what's the joy of guessing, I would say. So we see that, the x that will be changing. So we know that the values of x are going to increase as and when we move forward on the x-axis in the right direction. So how do you guys think this and this are going to change? Anyone? Is comparison that hard? And I'm even posing the question that is comparison even possible? So you can't say that, it's not quite possible and it might vary if something else happens or if something does not happen. So just go on. I want to hear all of you guys. What do you think about that?
So, ma'am, Pareto has an extra parameter alpha which is not there in the exponential. So, I'm not sure if comparison is possible.
I couldn't hear you clearly, but I see that you have made the point that Pareto distribution has some additional parameter alpha, right? Which is not there in the exponential. So we know that whatever the comparison would certainly also depend on the power that these is raised to, which is alpha here. So again, you cannot necessarily compare these two just wildly with the information that I have given you. So let me just break it to you guys. So if I'm plotting the exponential, again, I'm taking certain values for lambda, certain values for alpha, and certain values for x, which I do not want to write here. But what I want you all to focus is on the tails that I'm going to draw. So again, this is a bit tricky, but I'll try to draw as nicely as possible. So I'm drawing the exponential tail right now, and it will start somewhere from here, and it will go on till here. So we see that the probability is decreasing as and when you increase the value of x. Okay. And then if I were to draw the Pareto tail, I'll get something like, so yeah, initially it is lower, but then it becomes heavier than the exponential. Okay, so this is how you can have a look at, the upper tail of the exponential. So let me just maybe write it here. This corresponds to the upper tail. So here we are having a look at the upper tail of exponential distribution and the Pareto distribution. So again, if you have some data points and you plot them and you see that the tail is a bit heavier, so you can choose to, use Pareto distribution instead of fitting an exponential distribution. But if you see a normal regular kind of a tail and you see that exponential might fit better, so you can have the exponential distribution fit as well. But again, in some time, we will have a look at how to precisely determine what distribution would fit the best. And even after you have, modeled some distribution and determined its parameters, how to determine the best fit of any distribution and how to compare between two distributions which you might have, modeled for the same data set that you have. So now again, what will happen if, let's say, you don't observe either Pareto or exponential kind of a tail? So you might need something, which has a heavier tail than either of these guys, or even lighter tail than either of these guys. So that is where Weibull comes into the picture. And whenever I'm talking about Weibull, again, you might have guessed that I'm going to add some parameter to the distribution, and that will make it sort of Weibull type. So what I do here is the probability that my x will take a greater value than small x is e raised to minus lambda x in general exponential case. So I'll just add again a gamma parameter here. So again, this would be true for x greater than 0. So I'll add my gamma parameter here for this x to vary. So I think you all can see that, if your gamma value takes a value which is higher than 1, then you know that as in when you increase the x, this particular value is increasing in number. And if this gamma value is less than 1, this particular value is decreasing in number as in when you increase the value of x. So that will determine the kind of tails that you will have at the end here. But first, let us write the PDF of the Weibull distribution. And again, just, to not get confused, what we normally do is, instead of writing a lambda, you will write a C there. So, but it would just be functioning like a lambda, I would say. So now if I were to write the actual f of x, it would just be 1 minus this guy, right? So this will be 1 minus e to the minus cx raised to gamma. And can anyone help me with the PDF for this? So this is my f of x. And if I were to write my PDF for Weibull distribution, what will that be? Anyone?
So it will be the differentiation with respect to x, right? So
yeah,
minus of e to the power minus cx raised to gamma into minus cx raised raised to gamma into is it correct?
Not quite, right?
Or like what will happen to the x raised to gamma? Will we multiply it again? X raised to gamma minus 1.
So remember, whenever we have something, so let us start with, easiest step. If you were to differentiate e raised to 2x, what will you get?
2 into e raised to 2x.
2 into e raised to 2x. So what did you do here? You wrote this e raised to 2x as it is, and then you took whatever was there in the power and you differentiated it with respect to x for the chain rule, which is why you have this 2 here as the coefficient, right? So now can you guess what should be the differentiation over there?
So it will be c into x raised to gamma minus 1 into gamma.
Into gamma, right? Perfect. So I can write this again. So minus minus would go away, right? And I'll just write this coefficients in front. So I have c times gamma, x raised to gamma minus 1, e raised to minus cx raised to gamma. That's it, right? But again, now as we saw, we can actually compare the tail, the upper tail, so-called upper tail of exponential distribution and the Weibull distribution because of this thing that you have, and the only thing added is this gamma part. So now can you guys guess what will happen for two values of gamma that I can have? So again, I can have my gamma either less than 1 or I can have my gamma value greater than 1, right? So what do you think will happen in both of these cases? So again, here I'm comparing e raised to minus cx raised to gamma with e raised to minus lambda x. And here again, I'm comparing the same thing. So do you think here should be a greater than, less than, or equal to sign in both of these cases? What do you guys think? And again, this C could have, easily been lambda for the comparison. So for the purposes of comparison, just assume that lambda is equal to C.
Can you please repeat what your question was?
Okay, so I'm asking whether in this box I should write greater than, less than, or equal to symbol. So basically, I'm trying to see whether my tail of the exponential distribution is higher than Weibull or not. So essentially, because of this added new parameter, I know that there can be two possible tails, so one of them could be, lower than exponential, basically lighter than exponential, and the other could be heavier than exponential. So now I'm trying to figure out for what values of gamma do I get those two cases. So if my gamma is less than 1.
In the first one,
Yeah.
will it be greater than, like e raised to minus cx raised to gamma will be greater than the other one?
And why do you think it should be greater?
Because if gamma is less than 1, then like it's to the power, right? So
Yeah.
x will be as great as it can be. Okay, I'm confused.
Go step by step. So if your gamma is less than 1, what will happen to x raised to gamma? Will it be higher than x or lower than x?
Lower than x.
Lower than x, right? Can everyone see that? Lower than x, because my gamma is less than 1 and I know that my x is a positive number, not a negative number. So that's it. So now this is going to be a lower number. And when I'm raising e to the minus of something, essentially what I'm doing is 1 upon e raised to that number without the minus. So if I'm raising my e to a lower number in the denominator, it is going to give me a lesser value than it would have in this case. So that lesser value will be in the denominator. And when I transfer it to the numerator, of course, if I'm dividing by a lesser value, I'm going to get a higher value for the whole fraction. And which is why this, of course, would have a greater than symbol. And again, using the same reasoning, you would get the less than answer for this case. So now if I were to draw the tails of these guys, for the orange case where my gamma is greater than 1, I would have something like this. So it would start from here and it would go on and it would tail off really fast because I know that my gamma is greater than 1, right? So this would essentially be taking lower and lower values faster and faster. So see, for exponential, you are tapering off, but still not at the pace of this Weibull distribution. And for the next Weibull distribution, where we have a gamma value of less than 1, what happens is you start from the lower end and you will go and listen. I mean, it shouldn't be something like this. But I guess you guys get the essence, right? So yeah, it will have a heavier tail than the other guys. So this corresponds to lambda value less than 1. So these are the kind of flexibilities that you can add to the data by tweaking certain parameters or adding some parameters within the distribution function that you're given. So I hope this is clear to you guys. And again,
can you please repeat the inequality signs for gamma?
Inequality. Okay. So let us have a look at them again. So for Weibull, what do I have? I have e raised to minus c x raised to gamma. Okay, let me just write maybe lambda here. So I have lambda here. And for the exponential case, I have e raised to minus lambda x, right? So for any, let us decide the value of lambda is fixed, okay? It doesn't change. So now I'm taking my gamma value less than 1 for the first case. Let us see what happens. So first, let us compare this guy. If I'm raising x to gamma here, which is less than 1, and if I'm raising x here to nothing, which value do you think, Vanshita, would be greater?
X.
You think x will be greater? Of course, right? Because here x is raised to 1 and here gamma is less than 1. So I know that my x raised to gamma is less than x raised to 1. Perfect. So now again, add lambda. I can again add lambda on both the sides. It wouldn't change my equation, right? But now we know that we have a minus sign here as well. So if I add a minus here, what will happen to this inequality? So let's say, just assume, while this is not what the answer would be, but again, let's say this comes as 2 and this comes as 3. So you know that 2 is lesser than 3. And now if I add minus values, minus 2 and minus 3, what will this inequality be now? Vanshita?
It will change, it will be the other way around.
It will be the other way around, right? So now if I add a minus sign here, even this inequality would change to the other way around, right? So now I know that this power is higher than this power. And if I'm raising e to a higher power, it of course is going to take a higher value than if I'm raising e to the lesser power.
Yes.
So does this make sense?
Yes.
Okay, thank you very much for asking. Okay, so again, going back to this slide, I would say all that matters is not what's happening here. We mostly care about what happens in the upper tail, even of the upper tail, right? Because here we see that this Weibull distribution is a heavier probability than this, but yeah, those wouldn't matter. What matters generally is what happens in that region. And if you have a closer look, you see that all of these 4 graphs do have different sort of tails, and there is a comparison which you can always make. So you know which one of them would have a heavier tail and which one would have a lighter tail, right? And that will be used to fit the distribution, the kind of distribution that you would have. So again, whenever you're trying to fit a distribution, let's say you're looking at the losses, and what happens is here you will, let's say, have 2,000, 3,000, 4,000. 5,000, 6,000, and so on. So what company has to fear the most is the chance that it could incur a higher amount of loss with a higher probability, right? So let us say you don't fit this Weibull distribution. Let us say you are not even aware that this kind of distributions exist, and you only have Pareto and exponential with you. And if you fit the data set, you are most likely to fit the Pareto distribution. And even though here you don't see quite a bit of a difference here, but what happens is you are essentially underestimating the chance that a loss of 6,000 million could happen. And that you don't want to do. So to ensure against such kind of risks, what you generally do is try to have these flexible tails and see which one of these tails fit the best to the distribution that you have. And you do make sure that you are not underestimating, neither overestimating the probability of the occurrences of the events which could lead to a larger loss. So that is where these would really come handy. And again, we can try and derive the mean of the Weibull distribution. I think it's a good exercise. Let us try and derive the mean of Weibull distribution. Or do you guys want to take it as a homework? Because I think the next class would directly be on, Monday. So today is Friday and you guys do have Saturday and Sunday and the whole of Monday till the evening. So what do you guys think? So this would be the last homework that I give today, if at all this turns out to be a homework. Do you guys want me to do the mean of the Weibull distribution today in the class? Or do you guys want to take it as a homework? And then if you do have any problems, I can cater to them in the WhatsApp group, or else we can do cover it, in the next class as well. But if you guys want to try it out first, so again, what you will have to do essentially is you will have this PDF right here. You will just have to integrate this, right? With X, for expectation of X. Would you guys want to try it out for yourself first?
Yes, we will try.
Okay, what others?
Yes, ma'am. We will try.
Okay, just call me Kashmira if you guys can. I think that's much more comfortable.
Yeah, sorry.
But yeah, okay, so I see something in the chat, homework. Okay, yeah, thank you. So we'll have another homework added and try to figure out the mean of Weibull, okay? Okay, so now let us move on to the very interesting topic, I would say. It's method of moments. Do you guys remember it from the CS1?
Yes, ma'am.
And can someone summarize what was this about?
It was for finding out an estimate of the parameter used from a sample. Mostly.
That's actually a very accurate description, I would say, for the method of moments. You didn't even make a technical error. That's very good, Disha. Okay, so just to, I think this is interesting, and I think even if you already know about the method of moments, it's good to, have it in perspective of the random events that do happen within our lives. So have you guys ever traveled to the airport and thought that whenever I'm traveling to the airport, the journey seems a bit, shorter than when I'm traveling back from the airport? Does that happen with anyone?
It's the other way around actually. When we are going somewhere, it feels longer, and when we're coming back, it feels shorter.
Yeah,
ma'am.
so
I agree with that.
you agree with her? Okay. So do you guys know why is that the case? why does it feel like, it's taking me more time to go to the airport than while coming back? Any ideas? Okay, so maybe I would, just let you guys, I guess Vaibhav wanted to say something. Yes, go on, Vaibhav.
No, ma'am, no clue.
No clue. Okay, so I want you all to, think about it while we are discussing about method of movement. And again, it doesn't have to be statistics related. So you can have any wild guesses as to why that could be the case. But again, we'll move forth, and at the end of this topic, I maybe, we'll have the aha moment of why is that the case. I mean, I'm not sure how satisfied you guys will be with the answer, but let's see. So let us start with method of moments. And I think, again, it is just, we are trying to estimate the population parameters using the sample values that we have. So what kind of moments do you guys think we have? So the first is the mean of the distribution, and the second is normally the variance. And again, we know that, why was there even a need to have the variance of distribution? Like, why couldn't we do away with just the mean? So whenever I'm saying, why couldn't we do away with, that means to summarize a distribution, because we know that the whole distribution is a bit too much, to carry around always within our suitcases. So what we do is we try to have these moments, and we try to characterize the shape of a particular distribution using certain moments, which are peculiar to the distribution that we're talking about. And it could be a good way, to fit all the complexity that underlies the PDF within our brains, because we'll just have to remember certain numbers. And I think finding moments will help us to reach that goal. So the very first thing that we generally encounter is the mean of the distribution. So again, it depends on what kind of a distribution you're looking at. If it's a discrete distribution, you can have the mean something where you are summing up the xi's, which are weighted by the probabilities of each of them occurring. And you sum up across all the values of i's, right? And for the continuous case, you can again have the integration of x, f of x, dx, and this is over all the values of x that you can have. So this is how you would define the mean, and that could serve as, the purpose of characterizing a distribution. But why do you guys think we need the variance as well? Any clue? Because of course, even calculating the variance does add to the cost, right? And not only cost in terms of the time, but also in terms of the estimation of parameters and the degrees of freedom. Yes, Weibull?
Just to check how accurate the distribution is.
Just to check how accurate the distribution is. Can you explain me that a bit? Like, what do you mean by checking whether a distribution is accurate or not?
So variance essentially means the range of values, how far they will be placed, right, in a way.
Yes.
So maybe to see how, if the variance is lesser, it means that the distribution is more accurate. So just to find that.
Okay, so again, the idea that if your variance is lesser, the distribution is accurate. I think the kind of message that you want to convey is correct, but the way you said it is not. So whenever I'm talking about, let's say two distributions. So I have one distribution, something like this, and another distribution, something like that. So I know that the variance for this distribution is much higher than the variance for this distribution. Doesn't mean that this distribution is accurate. It's just that for some purposes, this might be accurate, and for other purposes, this might be accurate. So you can never essentially say that, one distribution compared to the other is more valuable until and unless you're defining the purpose that you're choosing this distribution for. Does that make sense?
Ma'am, can we also say that variance is used to calculate the mean squared error, and that tells us how good the estimate actually is?
That is a very nice point as well. So actually, yes, variance will help us to figure out the mean squared error. And what is the value of mean squared error? Do you remember? It includes bias as well as the variance, right?
Yes, and the lesser the mean square error, the better it is for us.
Yeah, the better it is. So is everyone aware of the mean squared error here? I guess that was covered in CS1. Or was it not? Okay, so again, what we are trying to do is we are trying to fit ourselves into the shoes of the person who came up with the idea of variance. So when the guy came up with the idea of variance, he or she, I don't know who that was, but again, let's just call it he was not aware of how it could be used in the mean squared error, right? The application of variance for the mean squared error was determined much afterwards than the concept of variance was even discovered. So again, this leads me back to the question that we have posed for ourselves. Why do we need the variance? Why can't we just do away with the mean? So let me just write it out. See, what happens is, let us say you have two kind of things. Maybe I can, so let us say we have this one and this is the another. Okay, so one of them is a disk and this one is a ring. So of course, if it is a ring, it has to be something like this. And the mass of the ring is distributed only here. There's a hole here. And when I'm talking about the disk, I know that its mass is distributed all across. These look like donuts to me and it just makes me hungry. But again, we'll try to focus on the concept that we are trying to study here. So if I ask you guys, what is the mean of this disk and this ring? What will you say? So I think we're used to, have not visualizing mean because we always see that there is a formula for mean, which is just summing up all the values and dividing it by the number of values that you have summed up. But again, that is not the only case where you see the mean. Try to understand what mean means in general. And can someone tell me what would be the mean of this disk and what would be the mean of this ring? So again, another name for mean is actually the center of mass. So the method of moments that we study is not actually something that statisticians came up with. We have actually, taken these concepts from physics, and it has a lot of applications in the laws of inertia, and there is a theorem known as parallel axis theorem, which this is analogous to and is mostly derived from, but we have just named it mean and variance for our purposes. So this is widely used in physics as well. And this application is from the physics part of it. So whenever I'm talking about the mean, what I essentially mean is the center of mass. Where does all of the mass center lies? So if I'm talking about this disk, I know it lies here. And if I'm talking about this ring, it again lies here. So although these don't look similar, but try to assume that these are similar. So if I try to figure out the mean, the center of mass for this disk and for this ring, it would be the same, right? And again, the purpose of having method of moments is to not look at the whole distribution. Just look at one value and determine some things about the distribution that we have or we possess. So if I were to look at the mean of these two guys, I would be confused, right? I would say that these both are similar objects, but we know that inherently they aren't. This is a disk and this is a ring. So even though the center of mass in both of these cases is the same, but the way the mass is distributed across is different. And that is why we need more information about these guys, and we cannot just do away with one value of the mean. So you need the variance, you need how this mass is distributed. So we know that here it is distributed only at the borders, and here it is distributed all across the disk. So again, what is the formula for variance, you guys? It will utilize expectation of x square, right? Minus expectation of x, the whole square. So this, and this is generally denoted by variance of x. Yeah, and that's it. And sometimes also, you know, I mean, that's, I shouldn't be, you know, writing that. It's like taking a particular, you know, side of normal always. So yeah, that's it. So again, variance is not one of the moments, I would say, but it is something that you can derive if you know the moments. So essentially my first moment is the mean, which is the expectation of x, and my nth moment will be expectation of x raised to n. So this right here is my second moment, this is my first moment, and this would be my nth moment. So again, you can go on and on about defining more and more moments as per the requirement of the analysis that you are asked to perform. So again, so this would be, so again, when I'm writing it in such a manner, it means that this is something which we call as a population estimate. But we know that we will have some data at hand, and we will be using that data to determine these moments. So if I'm looking at expectation of x raised to n, can anyone help me with what its sample counterpart could look like? So it would be something like summation of x raised to something. It will be x raised to n, right?
Into probability.
Into probability. So yeah, again, you can have, you know, x i's here and p i's here, and that would just be, you know, weighing it by the probability, by the chance of it occurring. And you will have this I across all the, generally you have n here, but because I've already used n, I'll just write t here. And you take average of it sometimes. Or sometimes you can ignore this n as well, like there's no hard and fast rule, because if you have this pi, you don't need this n. And if you do not have this pi, you will need this n. So remember that difference. Here, because we have taken the pi into consideration, you won't need the n over there, 1 upon n. So I hope that's clear about method of moments. So again, what we are doing is, in method of moments, we have some parameters and we have some values observed of the data set. So what you do is, you try to equate the population counterparts with the sample counterparts. So sometimes when you are given a data, you are given it in terms of, you know, numbers like 10, 15, 20, and so on. So you do not always know the PIs. It generally happens if you have a theoretical kind of a question. you will have PIs. And if that is not the case, again, I'll just write it for the sake of completeness because this is the definition that is given to you guys in your books. So summation I going from 1 till t xi raised to n. Okay, so this will again be, the sample estimate. So what you do is you have the data set and you add all of them and you divide it by the n and you will equate it to the expectation of x value that you already know. So what you can do is, let's say you are given some data set and you just take all the values and you average it. So that would be your value for the expectation of x, which you have observed, right? And now you again know that the formula for expectation of x in ideal scenario would be this. And again, you would not know the parameters of the distribution. You will just have a guess at what distribution it might follow, which is why you will decide what f of x should be here in the case. And then you will certainly have some parameters which are unknown to you initially. And if there is only one parameter, equating it to the mean would be all that you have to do. But again, if you have two parameters, the next thing that you can compare it with is maybe expectation of x squared or the variance. So expectation of x squared or variance, anything, but in softwares and everything, its variance is very handy. So you can compare it with variance as well. An expectation of x squared can sometimes be a bit tedious, but again, you might wonder that to calculate variance, you anyways have to figure out expectation of x squared. So you can do it either ways and you will get the same answer. But again, you just don't want to end up with more equations than the parameters, because then again, you might not have consistent results and you will just be, at a loss for what to do next. So in regards to the scenarios that we will be playing out within the syllabus, that will never happen. But again, if you are in the real world, you never know. So you have to take a guess as to, you might try various other numbers and various other cases because you'll be trying everything in a computer and it's only a matter of one enter and you can compare the results and everything else. So that was it about method of moments. And again, there is a bit of a ambiguity with if there should be a n or n minus 1. So again, there are certain cases where you should have n minus 1 and there are certain cases where n is much more efficient. So again, it depends, but mostly if we go with what's there in the book, they have used n everywhere. So we'll go with n. And that is all about methods of moments. So this is one of the methods to try to fit a certain distribution to the data set that you have observed. Is there any doubt regarding to this? Anyone? No? No or yes? No, thank you, Weibull. What about others?
No, ma'am.
No.
No.
Okay. Vanshita?
No, ma'am.
Okay, good. So I think you guys must have studied in CS1 about MLE as well, right? Maximum likelihood estimation.
Yes.
Okay, so can someone explain me what that is? Anyone?
We use the principle of maxima to find out the most appropriate value of the parameter or most appropriate estimate of the parameter.
Yeah, that's a good answer. That's a very good answer, Vanshika. Thank you. So what do you mean by the maxima principle?
The one that we studied in derivatives.
So you mean the case where you derivate a certain function and equate it to zero to figure out at what value the function attains its maximum value?
Yes.
That's correct. What about others? Does anyone have anything else to add about maximum likelihood estimation? Like, why is it called the method of maximum likelihood, Why can't we have a method of minimum likelihood or the method of moderate likelihood or something? Has anyone wondered that?
No, ma'am.
So
Maybe because we want the most appropriate estimate,
define appropriate.
which is most likely to happen.
What is most likely to happen? The parameter?
Which is nearly the exact value of the parameter.
Okay, so you say no. So can you say that again without using appropriate word and defining what appropriate means for you?
The value of parameter, which is the value we find the estimate which is nearly equal to the parameter.
But how do you check whether it's equal to the parameter or not? Because to start with, you don't know the parameter's value, right? You are just finding it out by using MLE.
Okay, I don't have answer for that.
See, I think what you're thinking is correct, but you just don't have words to explain it. But I can sense that you have some idea. What about others?
So ma'am, when we do the double differentiation in this method, we go for the answer that is greater than zero, right? Like we just check that our answer is greater than zero. That is, we are finding the maxima. If our answer is lesser than zero, then we consider it as the minima. So our parameter can't be minima, right? Like it can't be less than zero. Our parameter can't be negative basically. So instead we go for the maxima, that is just a way of saying greater than zero. Hello, was I audible?
Ma'am, are you there?
Oh, I think I was unmuted. Oh my God. So whatever I said, you guys didn't hear, right? So, okay. What I asked Isha was, I pointed out a certain thing in your answer where you said, that the value of the parameter will be less than 0 if you get the double derivative's value less than 0. So I was asking, what do you guys think about this? Because what I want to ask now, again, a different question based on Isha's answer, is that if I get the value of double derivative evaluated at the value which gave me the 0 derivative in the first place, well, if that derivative evaluates to be less than 0, does that say something to me about the parameter's value itself or something else about the parameter?
It tells us about the function, right?
It tells you about the function, right? Not about the parameter. Good. So again, now, why don't we have the minimum likelihood estimation?
Ma'am, I didn't understand your last question.
Okay, so Isha, what I said was that if you are, let's say you did some calculations on a function and you took the first derivative, you equated it to 0, you got some value for the theta, let's say that is your parameter. So you got some estimate for the theta, right? And then if you, let's say, double derivate it and you got the double derivative evaluated at the theta, which you derived in the first case, less than 0, you will know that, I have essentially minimized something. So when I'm saying that I have minimized something, that fill in the blanks for something would not be the parameter. That would be the function itself. So what I'm essentially saying is that at this, give me
Oh,
a second.
understood. So like the final value of the equation, the whole equation will be maximum or minimum.
Yeah, exactly. The whole function will be minimized, right? Not the parameter. Perfect. That's good.
Understood.
So again, that brings me back to my initial question. Why don't we look at minimum likelihood function or moderately likelihood estimation? And why do we care only about the maximum likelihood estimation?
According to me, minimum likelihood method would mean that the estimate that is least likely. I don't have the words, the right words.
I think I do understand your plight. You do understand what it means, but you don't have the words.
Is
Does
it because
anyone
the
else?
objective
Yeah.
is to find the most probable estimate of the parameters so that it will help our calculations and the distribution. So that's why we
Okay,
find
so
the maximum likelihood.
the objective is to find the most probable estimate of the parameter. Does everyone agree with that statement?
Yes.
Yes.
Okay, so I would say that I do not agree, and let me show you guys something, and then you guys decide it for yourself, okay, whether that's true or not. So let us start with something. Okay, so again, we have something with us, and again we have something else with us. So in my first circle, I'm going to write something like reality, the thing which it is in the actual case, and the population. And here I write that I have a data sample. Okay, so sometimes what happens is that you're given a data sample and you have to try to see whether it fits the reality well or not. And in some cases, you might already have some modular population which is specified, and you have to see what is the chance of observing that particular specifics in the real life. So again, I'm talking about two different things here. So does anyone know the difference between probability and likelihood? Or are these terms synonymous to each other, or are they similar, or are they equal? And these three terms again mean different, okay? One thing could be similar but not equal. Some things can be similar, equal, and synonymous. So yeah, what do you guys think is the relation between probability and likelihood? And again, why do we have maximum likelihood estimation and not maximum probability estimation or something like that? Any idea as to what is the difference between probability and the likelihood?
Is it like probability is like possible results and likelihood is something related to the hypothesis?
So you say that probability is about results. Results of what?
The experiments or the data that we have.
Okay, okay. And likelihood has something to do with the hypothesis. But that still doesn't, ring a bell as to why there should be two terms like probability and likelihood. I mean, has probability nothing to do with the hypothesis testing? Anyone? Okay. Okay, so maybe what we can do is, let us first see the difference between the probability and likelihood of some function that we have. So I have a certain graph here. Let's say I have something here, and this is how my PDF looks like. So I'm taking it to be normal. And again, are you guys aware if, so let me just ask you a random question. Is MLE only useful in the cases where we are dealing with the normal distribution? Question mark. Yes or no? Only normal or not only normal? Anyone?
I think it's used in non-normal distributions as well.
Yeah, it is used on normal distributions as well. So that's fine. I mean, MLE works everywhere. And so I guess you guys have heard of R.A. Fisher. He was the guy who was claimed to have come up with the concept of maximum likelihood estimation. Apparently, when he was just 23 and he was in his undergraduate during that time. So I think, yeah, he was quite a genius at it. And there is a bit of a history of maximum likelihood estimation. And there's a nice paper by Stigler. It goes by the name of the epic story of maximum likelihood. I don't know if it has the word estimation at the end of it or not. But yeah, again, coming back to our question, the difference between probability and likelihood. So whenever I'm talking about a probability, let us say that I'm looking at a normal distribution, just for it to be easier, that the mean of whatever I'm looking at is 32, and the ends, it can be 24 at one end, and let us say I'm assuming that we have 40 at the other end. Okay, and again now I have defined my mu here. So I have written my mu to be 32, and I have my sigma as well, which takes a value of 2.5. So if I write something like this, so let's say if I'm writing that I want a probability that my x random variable, which I've plotted on the x-axis, takes a value between 34 and 32. Given that I'm looking at this normal distribution, and a way to characterize this normal distribution is through its mu and sigma, right? How can I plot this on the graph here? Anyone? So let us say I have 34 somewhere here. Any idea as to how can I plot this probability on this graph here?
The area between 32 and 34.
The area between 32 and 34 and under the curve, right?
Yes.
Well, so I just take this up there, take this up there, and I know that my probability is all the area which underlies here. So just to give you a perspective, the answer to this comes out to be 0.29. Okay, so again, you know that we have used the parameters of the distribution to figure out the probability, the chance that we will observe something that we have defined here to be more than 32 and less than 34. So that's it. And now in the next case, I want to define something else. So let us say here, I'm already assuming, so just to define this again, we're looking at the same graph. So here, what I have done is, I have already observed my value for x, and that turned out to be 34. So this is the observed value. So now the question that I am asking is, given that I know the value of my x is 34, which normal distribution curve would fit well? So again, I'm not necessarily saying here that the normal distribution that I have drawn with mean 32 here is the best, okay? But again, this could be one of the plausible distributions that I can have. And the one which I have drawn here in black certainly has mu of 32 and a sigma of 2.5. So what I'm doing here is now that I'm trying to look at the chance that I will observe my x value to be 34 under this normal distribution. How would I plot that chance on this graph? Anyone? Where on this graph can I plot that chance of observing x equal to 34 given this normal distribution?
On the curve, maybe.
On the curve. So what should I do on the curve? So I'll just take this up there. Let me use the red. So I'll just take this up there and take it on the y-axis here. And what I get here is 0.12. So this would be my answer. So this would be my answer to this question right here. the chance that I will observe my x equal to 34 under this curve. Okay, so again, what I can do is I can actually change this curve, right? Because if I give you guys one observation, so I've only made one observation for my data, and that turned out to be x. So x took the value of 34. So what distribution or what parameters for normal do you guys think would fit best to this kind of a case? Anyone? What should be the parameters of my normal here? If I want x equals to 34 to be most likely to happen, what should be the mean and what should be this?
Then the mean will be 34.
Exactly right. The mean will be 34. And what about variance?
I think the variance will be more, or it
Okay,
will be
so,
the same.
Okay, so in ideal scenario, you would have wanted the variance to be 0, right? Because then what you have observed is 34 for 100% cases. And then if your mean is 34 and the variance is 0, essentially you would mean that the curve is just here. The model that you have fit will also be seeing the same thing, that 34 will be observed 100% of the times, but then it wouldn't be normal distribution, right? So you need to have some sort of variance. So for this case, let us assume that the variance remains the same. Then if I keep my mean as 34, so now if I'm looking at some normal distribution where my mean is 34 instead of 32, I will have this graph peaking at 34 instead, right? So this graph would essentially be the same, but just, oops, that was, so it would have to shift a bit to the right? Because I have now said that my mean is 34. So that should be the value here. So now, if you observe the chance of observing 34, it turns out to be pretty higher than what it was before. So this turns out to be 0.21. And so this is how we can differentiate between probability and likelihood. So of course here I have written P and here I have written L. So this means probability and this means likelihood. But can anyone now try to guess the difference between probability and likelihood? So one difference could be, probability is the area and likelihood is the value on the y-axis. So again, what is the other distribution? Oh, sorry, what is the other difference? Or in general, how would you classify probability and likelihood? Anyone?
The likelihood is for the parameter.
Likelihood is the parameter, okay. That is a step forward, yes, but not quite there yet.
Is likelihood the probability of, like, or something related to the sample, like that sample should happen. So we want the maximum probability of those particular values taking place.
Exactly. That is exactly right. So now do you guys see why do we need the term maximum likelihood estimation and not minimum likelihood estimation? Anyone? Can you guys answer that question now?
Can you repeat the solution, please?
What should I repeat, Weber?
So what she said right now, I couldn't catch that.
Okay, so what she said was, Isha, can you just go at it again? Can you say that again?
I said that likelihood is where we want the highest probability for that sample to happen. I don't know how to put it into better words. Like
This
is just a
this
rough
is the
thing.
best you can do. I mean, yeah, it's good. It's good. Don't worry, it's good. So yeah,
Thank you.
I think we have interesting answers. Yes, Vaibhav.
I just said thank you.
Oh, okay. So again, now do you guys have the answer as to why should we look at the maximum likelihood estimation and not the minimum? I think it has to do something with what Isha just said. Mihir, what do you think?
I have a question first. For likelihood, as she said, it is maximum probability of that sampling occurring, right?
Yeah.
And then what is the meaning of probability? Is that what particular value that X is taking? It is like that.
Okay. So let me just, break it down a bit again. So what I'm saying when I'm talking about a probability is that I have some parameters defined for my population already. And I'm trying to figure out something about the data that I have. So I know something about my distribution here, and I'm trying to figure out some information about the data. And information here being what is the chance that my data will lie between 32 and 34. And when I'm talking about likelihood, what happens is I have observed the data already. And now I'm trying to see what happens or what parameters of the distribution would make this data point or this data that I have observed the most likely to happen. So here we are modifying the shape and the location of the distribution, and the measurements on the RHS here are fixed. But here we have already defined the shape and the location of the distribution, and we are just trying to determine some information. Does this make sense?
Yes.
So again, if I have to, let's say, summarize, yeah. So again, if I have to, just summarize in short, what I can say is that my probability is something where I have information about the distribution it follows, and I'm trying to figure out something about the data that I have at hand. And when I'm talking about the likelihood, I know something about my data, which is what I have observed, and I'm trying to figure out what distribution fits it the best. So I hope this certainly makes it clear that this way is the probability and this way is the likelihood. Does this make sense?
Yes.
So I think you can always use maximum likelihood estimation even without knowing all of this stuff, okay? You wouldn't be bothered much about it, but again, I think it's very essential and crucial to know these sort of differences, because when you're trying to, write reports or something else, I think the word choices that you do make would matter a lot. Not that those CEOs and those would understand this subtle difference between probability and likelihood. For them, it would be the same. And again, whenever I'm talking about probability and likelihood, these terms are loosely interchangeable. You can use them instead of one another, but you do know that there is some sort of deeper distinction between these two concepts that we are studying. And why do we have maximum likelihood estimation? Because all the other times you're talking about probability, right? We never talk about likelihood. And why here suddenly we want to care about the likelihood? And is it any different than probability? So again, just to answer my question, why should we not have, minimum likelihood estimation? Is because what's the point of even looking at minimum likelihood estimation? Because let's say if I define something on as minimum likelihood estimation, analogous to as you are defining maximum likelihood estimation, what it would mean is, given that I have observed my value of x34, what parameters should I have for my distribution to be 100% wrong about this information? Because that is what it would essentially mean to have a minimum likelihood estimation, right? I want the chance to be lowest to observe what I have observed. And does that make any sense? No, right? So you want the maximum chance to happen for what you have already observed in the distribution or for the distribution that you're trying to fit. Does this make sense? Some clearer idea do you guys have now about the purpose of MLE?
Yes.
So yeah, I think it also helps to know about why are we doing the things that we are doing, and that would, maybe not help you directly, but indirectly at some point I think it does. So again, now if once this is clear, I think again, what is the one crucial step that you guys must have been really encountered while maximum likelihood estimation? What do you guys also use along with it? So whenever you define a likelihood, let us say we have some observed samples. So let me maybe write it down. So I'm saying now that I have observed some sample which comprises of X, and all the data values are, determined with small x's. And what I again say is that, now I will define the likelihood function. Does anyone have any idea how should I define the likelihood function? How do you define the likelihood function? Anyone?
It is a product of all the probabilities.
Yeah.
Exactly right. Thank you very much, both of you guys. So we do the product of probabilities, but is that what should we do? So again, whenever I'm talking about likelihood, what do I mean? Do I mean the likelihood of observing only one particular X value, or do I mean the likelihood of observing all the values of X? Question mark. What do you guys think? Only one value of X or all the values of X?
All the values of X, right?
All the values of X, right? So essentially what I should be writing for the likelihood is the joint distribution of all the observed data points that I have, right? So again, if you guys remember the theoretical and more accurate definition of writing a joint distribution, it comprises of conditional probabilities. Even when you derive, this likelihood estimates, you do encounter conditional distributions. But just to make our life a bit simpler, we make an assumption that all the data points that we have generated or we have observed are independent of each other. And that is what allows us to just write the likelihood function as the product of marginal probabilities. So what I'm going to write now is assuming that all of my x's are independent of each other. So let me write that assumption first. Assuming that my x's are independent, I can write my likelihood function as the product where I goes from 1 to n and I have xi's theta. So again, in some textbooks, or I think even in your actual textbooks for actuarial sciences, they have, so what they do is, instead of writing this semicolon, they will have something like a dash here. And I think it's only, not, I mean, it's not that it's inaccurate, but it's just that it's deceptive. Because when we write something like this, what we assume is we know something about theta, and now we're trying to figure out something about x, which is not what likelihood is, right? We know something about x and we are trying to figure out the theta. So I would suggest all of you to always use this semicolon and not the dash. So yeah, just, to make the idea of likelihood clearer in your mind. So again, here we know that all of my x's are independent. So I have to take a product of this. And again, when I'm defining only one function f of this, I'm also assuming that these are identically distributed with the function f of x, right? So that is the assumption that I'm mostly making, that they are IID. And then I can write this likelihood function. So now what I want to do is, I want to maximize this likelihood function, right? I want it to take the highest value possible. So what will I do? I'll differentiate it, right? With respect to what? Theta or x? Anyone? What will I differentiate this likelihood function with?
With respect to theta.
Right, with respect to theta, because that is the parameter that we are trying to maximize the likelihood of. I mean, not exactly the parameter, but that is what is unknown to us. And the data that we have is in a way dependent on the parameter's estimate as well. So the parameter would in a way define the observation that we will have for the data point within the model that we have fitted. So again, do you guys remember that we do not generally, maximize the likelihood itself? What we maximize is something else. Does anyone remember? What do we maximize?
Log of likelihood, right?
Log of likelihood, right? And why do you guys think we only maximize the log of likelihood, not something else?
In log, everything gets separated into addition or subtraction, and it becomes easier to differentiate. And the answer is always the same as normal differentiation.
And why is the answer always the same?
I don't know that.
What about others?
Not sure.
Did anyone try to say something? Anyone? Why do we get the same answer if I maximize a function or if I maximize the log of the function? Like, why can't I just take, the absolute or E or something else? I mean, that wouldn't necessarily separate these functions, but again, why log? What is special about log? Anyone?
Is it because the shape of the function remains the same or something like that?
Quite a bit there. The shape of the function actually doesn't remain the same, but the way it behaves remains the same. So whenever I'm talking about log, what happens is if I increase the value of log, and when I'm saying I increase the value of log, I mean whenever I'm increase the value of x in log x, I know that my log of x will also increase with the value of x. It will never decrease. Okay. And here, remember, we are trying to talk about maximum likelihood estimation. So what happens is, whenever you increase the value of x, the log of x will increase. And if you decrease the value of x, log of x will decrease. And this property is known as monotonically increasing. So whenever I'm talking about a log function, I know that my log function is a monotonically increasing function. Have you guys heard of this word before? Monotonically increasing. Anyone? So generally,
monotonous is something that keeps on happening continuously, right? It just goes on and on.
Yeah, exactly. And this is actually just another name for monotonous. So this is monotonically increasing. So it is continuous. It doesn't break off for some excess value. So we know that if I'm trying to, if let's say if I'm wanting to maximize my likelihood function, which is right here, for the same values of x, that will maximize my likelihood function here. The same value of x will also maximize my log of that likelihood function here, because it is a monotonically increasing function. So whenever I'm saying that, what I mean is, let's say if I observe some x like this, okay, and if I take the logarithm of these guys, I will get something maybe like this. Okay, so, and let's say this was A, this was B, and again, this should be A and this should be B, right? So the maximum here again is at B, and here as well it was at B, but just the values that the function will, this is not the log that you would get, but just to show you guys, this B point will be the same, but the likelihood here and here may not be the same. So again, that is one of the reasons, because see, if you have some C here in between this value, I know if I apply log, again, the value will be in between A and B. It wouldn't go, something like this and then that. So that the value for some guy here is much higher than it was at B, and it wasn't, that higher here or lower. So for C here, you observe a value which is lower than the A value, but here you do observe a value which is of course higher than the A. So you cannot have a graph like this which is not monotonously increasing in its properties. And again, log also simplifies the calculation a lot. So because these multiplications would only render x power something. So it's easier if you apply log. So what we have a look at is log likelihood. So if I'm applying log to my L here, which is a sum, what I would get is which is a product. What I would get here is the sum from 1 to n of, again, f. Does this make sense to everyone? So again, I'm writing a sum here because I'm assuming that the distribution I'm looking at is a discrete distribution. So again, so let me ask you guys this question. Will this sum change if I have a continuous distribution?
If it's continuous, will it become integration?
That is my question. Will it or will it not?
I think it will.
I think it won't.
And why do you think so?
Because the summation is because of the product. We are taking the log of the product. So that will remain summation only, right?
Yeah, exactly, right? That is correct. That is correct. Don't worry. I have this habit of, just asking trickier questions just to see if you guys are awake or not. So it wouldn't
And
change to integration?
shouldn't
Yeah,
it
someone wants to.
be log
Shouldn't it be what?
of function?
Yes, exactly right. It should be log of function. Thank you very much, Manshita. It should be log of function, right? Well done. Okay, so that was it. And now if you want to, maximize, so again, I will just write to maximize the log likelihood. What you do is differentiate this log L with respect to theta and equate it to 0. And to check maximum, they should be less than 0, right? Is this clear now? So I think let's just, so I hope you all are already aware of how to solve the maximum likelihood questions. But maybe what we can do is just have an example of you guys walking me through some question that I will just write now on the board. Okay, so I'm saying that, some blah, 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 blah. So let me just define that blah, blah. So let us say we have an insurance company which uses an exponential model. So we know that they will use exponential. So they do use exponential distribution to model the cost of repairing insured vehicles that are involved in accidents. And what you have to now do is find the maximum likelihood estimate of the mean cost given that the average cost of repairing a sample, so the mu is, so they are saying that the number of vehicles are 1,000 and the average cost of repairing a sample of 1,000 cars was 2,200. I mean, you can ignore the pounds and all those values. But now what I have to do is, I have to try to figure out the parameter of my exponential distribution, given that I have observed so and so. What do you guys think I should do?
Ma'am, can you please repeat your question?
So I said that I am looking at a company which uses exponential distribution to model the cost of repairing vehicles. Okay. And they say that the average cost of repairing 1,000 vehicles is 2,200. Okay. And what you have to now do is find the maximum likelihood estimate of the mean cost. What should I do? So basically, I have to figure out what should be the estimate of the parameter for the exponential model. So let us start with this question. What is the parameter in the exponential model? And how many parameters do we have in the exponential model? Anyone?
One.
One parameter, right? That is lambda itself.
Yes.
Okay, so now what should I do?
Write the function.
So what function should I write? CDF or PDF?
PDF.
So my f of x now is lambda e to the power minus lambda x. Okay, that's done. What should I be doing next?
Substitute the values.
Substitute the values where and for what?
Lambda will be 1 by mu.
And how do you know that?
Because the mean of exponential is 1 upon lambda.
It is 1 upon lambda, right? Okay, so mean of the distribution is 1 upon lambda. So what should be my, so I know my x bar here. What is my x bar here?
0.5.
2,200, right? So if I am to talk about the estimate of lambda that I have to look at, it is what? 1 upon 2,200, because this is my average cost. Does this make sense?
Yes.
Okay, so but again, you know, if to do this sort of a thing, we have used the fact that I already know that my x bar will take the value 1 upon lambda. And how do we know that 1 upon lambda is the best estimate for x bar? The mean, basically. So let us try to, utilize what we just studied, the theory of maximum likelihood estimation, and define the likelihood function for this example. So if I were to write my likelihood function, how would that be? Anyone?
Product of f of x. Right.
Product of f of x, right? Let us start with the basics. So I'm taking I from 1 to n, and I know that my n here is just 1000, right? And I'll write my f of x here. And this is how I define my likelihood function. And what should I be doing next? Anyone? So again, just for general purposes, let us not define what our value of n is as of now. Let's keep it n. And then at the end, we can substitute the value of n. What should I write next?
Do you take the log likelihood right now?
You can't take a log likelihood right now. That's
But
correct.
we would preferably simplify it first.
Okay. And how would you simplify it, Vanshita?
Would it be lambda raised to n into e raised to minus lambda into summation of xi?
Yeah, so yeah, I forgot to put I there. So what we have is xi's where I goes from 1 to n. So I'll do this for x1 and I'm multiplying this again with lambda e raised to minus lambda x2 and so on till xn, right? So what I do is I take all of these lambdas outside of the brackets. And how many lambdas do I have? N. So I'll have lambda raised to n. And then if I have something like e raised to minus lambda times e raised to minus lambda, I know that e raised to a times e raised to b is just e raised to a plus b. So what will I have here instead is e raised to minus lambda x1 minus lambda x2, so on till minus lambda xn, right? And what should I do now? Anyone? Can I simplify it more?
E raised to minus lambda common in the bracket x1 plus x2 till xn.
You can just write summation xi, right?
Yeah. I can also write it as summation xi. That's correct. And is there any more simplification? Any other simplification that I can do?
No. Now we can take the log likelihood.
Yeah, take
Okay.
the log and then derivation.
So let us take the log L. What will I get for log L here? Anyone?
N lambda minus lambda summation xi. That's it.
N lambda minus
N log.
Oh, sorry, n
n
log.
log.
Bye bye.
Exactly. It should be n log of lambda. Okay. And then
Minus lambda summation x.
perfect. And now what should I do?
Derivation.
Differentiate.
With respect to
Lambda.
and what will I get?
N by lambda minus summation of xi.
And now what should I do?
Equate to 0.
Equate to 0.
So again, I'll equate this to 0. And what will I get? And again, remember the crucial step is also, to put a hat on the estimator, right? When you equate it to 0. Because whenever you're equating it to 0 to figure out its value, you are using a certain sample, right? Which is clearly not the whole of population, but just a representative of the population. So you have to take care that the lambda value that you will get will be an estimate, not the population value of lambda. Go on.
Lambda hat is equal to n upon summation x.
X. So lambda hat is equal to what? N upon summation xi, right?
Which is 1 upon
And which is just 1 upon x bar. So I know now that this is how I can define my lambda hat, and I know my x bar is just 2200, which is why the value of lambda hat in this particular case will be 1 upon 2200. And is there something else that we should do?
check that maximum.
Exactly right. We ought to check whether what we have derived is indeed the maximum or not. So what should I do?
derivate it again and see if the value is more than or less than 0.
Yeah, so I'll have to derivate this guy again. And what will I get?
Minus n
Minus n
by lambda square.
upon lambda square, right? And is this greater than or less than 0?
It's less than 0.
Right, because squared something is less than 0 and n is a positive number, which I know here is 1000. So minus of some positive number is of course to be less than 0. Therefore, indeed, it's a maximum. Okay. So I hope that's clear. And this is how you can use the maximum likelihood estimation. Does this make sense? Does anyone have any doubts with this?
No, ma'am. Yeah.
Any questions regarding why is something the way that it is or something else?
Ma'am, are we doing this just to brush up our basics, or just is this a chapter in the subject itself?
So this is actually in the chapter called loss distributions. So they do, go through all of the distributions and how you do the MLE. And then in the next chapter, we will be studying something about the method of percentiles and the goodness of fit. So I do think that, this is important to get these concepts a bit clear. And that is where your first chapter will actually end. But then this is just studying a bunch of tools and techniques. And maybe it is for revision, I would say, but I think it's a good revision.
All right, thank you, ma'am.
Anything else? So I would say that's it for today. And next lecture we will have will be on Monday. And again, I will, put the PDF in the group. And yeah.
Thank you, ma'am.
Thank you very much.
Thank you.
Have a great day. Have a great weekend, actually. Enjoy.
Thank you.